Hello, Calc 2 students. Today, I'm sorry I'm coming to you through a video. I'm with my son at a campus visit. He's a junior, so he's looking around at different colleges. But Annie's going to help you with some examples at the end, and I thought I'd do this introduction at the beginning to launch you into Chapter 7. We're going into Chapter 7 that's going to cover all of the different methods of integration. And we're starting today with one of the biggest methods. So this is a really important method, the substitution method. It's used in a lot of the other methods within the other methods, and so it's one that you're really going to want to learn and master. So let's just step back a minute and look at this chart at the top of the handout. So far, if we're going to integrate something, we know that the fundamental theorem of calculus has some different shortcuts that we can use, and we went over those and had a chart of those. You tested on some of those on the test yesterday, and so we know some of the basic ways of antidifferentiation. And the fundamental theorem of calculus is great if we can do that, but we said that we can't always do that. You can't always find an antiderivative, so then we learned how to use numerical methods, and that's why we did the first project. Because we knew that we're not always going to be able to antidifferentiate. So sometimes we need to numerically integrate. So in this chart, I just wanted you to stop for a moment and see, maybe right to the left of the chart, a few of the ways that we numerically integrate. Just quickly write down those 5 methods. And then once you write down those 5 methods to the side, then see if you can go ahead and fill in the chart. See if you can think. We've got 2 columns here. One for algebraically defined functions, so that would be like the first half of the project where you were given functions of the form f of x equals some expression. Think about within those types of functions, what is your single best estimate and what would be your interval estimate. What's the smallest, what's the largest, or something that you know is going to be below and above the actual value. And then the next column, think about functions that are given to us in a data form. When you worked with your groups and you collected your velocity data or other rate data, what was the best single estimate that you would use and what is your best interval estimate? I'll give you a moment to kind of write those down and think about those, and I'll write them here to the side. And fill in the chart and see if you can figure out what those are, because that will kind of wrap up our numerical methods and make sure you understand from now on what you would use if you had to go that direction, because we're going to think about these numerical methods as somewhat in our back pocket as a tool that we can pull out whenever we cannot algebraically antidifferentiate. So I'm filling in the chart. You fill it in as well. Okay, I'm not going to give you long because I hope you know this very well. Under algebraically defined functions, for the single best estimate, we know that Simpson's rule is the best numerical method that we have. So if you had to come up with just a single best estimate, what's my best estimate for this antiderivative, you would use Simpson's method. If you had to find something that was for sure underneath the actual value and above the actual value, you would use trap and mid to give those estimates, because they're the tightest interval that you could give. For data, the single best estimate would be trapezoid method, and if we needed an interval here, we know that we can't use trap and mid. Why was that again? I hope you remember that midpoint rule. We can't go halfway through an interval when we have data. So therefore, we're just left with left-hand sum and right-hand sum, although they weren't as good over here with algebraic methods. For data, those are going to be the best methods we can use. So that kind of concludes that piece, and you might remember that all of those numerical methods were off in section 7.5. That's at the end of the chapter. We actually started with that just because we realize I'm not going to be able to algebraically antidifferentiate everything. Therefore, I'm going to need these numerical methods in my back pocket. So don't forget those. Those are kind of in your back pocket ready to go. So today we're starting again into Chapter 7, the rest of Chapter 7, where we're going to march through several of the different methods for antidifferentiation. And this first one is called substitution method. And I'm going to just go off to a PowerPoint right now to just go off and take a little break and a little side tour. So we're taking a short break from calculus for a reality check. When we get caught up in our due dates and stressors, it's good to take a peek into other corners of the world. So you just got done with a big test and a project, and you're still working on your take-home, but it's a good moment to kind of pause when you get stressed out and think about what's going on in the rest of the world, that it's not all about us. So you can do that by focusing on different places. Sometimes it gets overwhelming to hear about all the different things going on in the world, but we're going to look at Congo. I've told you that I have a special place in my heart for Congo just because my brother and his family are missionaries there. My brother is an MAF pilot there, so we keep up with things going on in Congo. So I'd encourage you to do that as well. Sometimes you can get overwhelmed with all the different things going on all over the world. You should be aware of what's going on in the world and not stay in the Bethel bubble. Get out of it and understand some different communities, different places in the world, and pick a few that you might focus in on and follow and keep up with what's going on in those places, just to kind of give yourself a reality check here and there, to remind yourself of all of the needs in the world and the things going on in the world. So I'm going to show you a few photographs and some words here. I'm going to go quickly through this, but I'll put this up on Moodle so you could look through this a little bit more carefully if you like. But this will just show some of the needs that exist in Congo and then also the hope. So the pieces that I'm going to show you are taken from a National Geographic article that was a really nice summary called The Price of Precious. The minerals in our electronic devices, so in your phones, have bankrolled unspeakable violence in the Congo is one of the big bylines of this article. And there's a link there if you'd like to look at that further. But I'm going to show you a few of the pictures from that article because I thought the photographs were pretty amazing as well. So this first one is the desperate for safety. These villagers are fleeing, fighting. My brother's been involved with several missions to go and help refugees in various places. The next one, patients wait for medicine that never arrives at a health clinic. The rebels won't give charity agencies access to the clinic. So just understanding some of the conditions that exist in various places, we take for granted our medical, or the ease that we have for getting medical attention in our lives, and how desperate and some of the conditions that exist in other places. The next one, schooled in conflict, child soldiers patrol this gold mine. So it's so sad to see this as well. Children carrying these big weapons. And next to a boy waits his turn for spoonfuls of rice and beans in Pluto. In some areas of eastern Congo, up to 40% of gold miners are children. So Congo in particular is very rich in its resources, but they've been exploited so much by other people, by other countries, and then just these militias that take over all the resources and force people into labor. And then the last one's really terrible. I read some more statistics last night, even with how this has even increased since this statistic. It says a woman left for dead faces a long recovery at a Hope in Action shelter in Goma. A 2007 study estimated that more than 1 million Congolese women have been raped at least once in their lifetime. So it's pretty amazing. The eastern part of the country, there's just continuous fighting, and it's called the rape capital of the world, so very desperate situations. Then from the same National Geographic article, there was this quote: when we asked him, a UN, so United Nations official, what it would take to fix Congo, he looked down at his polished shoes for a long time. There's no easy solution, he said, and I'm not even sure there is any solution. So very desperate conditions. But what I wanted to also bring to you is that there's hope, both in action and in Christ. So we as Christians do have hope, and we can have action as well. I loved this article Tech giant Intel on Monday announced that its entire 2014 line of microprocessors would be free from so-called conflict minerals, making them the first in the rare mineral heavy industry to completely phase out their use in one of their products. So we can take some social action to change some of these directions. So imagine you being in a company that's going to stand up and say, we're going to do some research, find out where some of our resources are coming from, and make sure that we're not supporting some of these actions in places like Congo, where it's supporting these child slaves and other things that are going on. And then here's a picture. I showed you this picture, the one picture of my brother on the first day of class, but this is also just an example on how you can make a difference. So my brother has been serving in Congo for many years now. I was able to fly with him when I went and visited to this particular village, so you can see the people waiting there underneath the plane wing when we arrived. And this next picture was really meaningful to me. The guy in the yellow shirt is the missionary that was there, and he pointed out this girl in the pink shirt in the middle and said she wouldn't exist if my brother weren't here. She was a twin, which if you have twins in a place like Congo, it's really rough. We know here we have all kinds of medical care. If there's a preemie, we just immediately put them into the intensive care unit. But there, it's a hard deal. So my brother was able to fly her mom out quickly to another medical place where they were able to have better medical care, and she lived. So that's encouraging as well, even to save one life and allow her to have life. It was a big deal. So it was fun to see and not only hear about all of the various things, but to see an actual person who was touched. So there's many more stories. I'd love to sit here and talk with you more, but I need to move on to the topic for today. And so I'm moving on to a story of a particular bumpy ride that my brother had. This was in February of 1999. They were living on the eastern part of the country, and Garth and his family had to flee because of rebel fighting. In Congo, the reason they need planes so much is the infrastructure is very poor and the roads are not good. You can see some of these pictures with that UN Jeep stuck in the mud. That's kind of a common piece. So families flew out, leaving behind their house and most of their belongings. Garth and another pilot took a few things out by driving a vehicle and a motorcycle. So my brother was on this motorcycle driving behind the vehicle so that they could try to escape the rebels that were coming quickly, who ended up raiding all of their and taking all of their belongings that they left behind. They wanted to get out as much as they could. So this function that I'm making here today is going to be in tribute to Garth's motorcycle ride. So the ride itself took 151 miles, 11 hours to get there. They were basically driving out of the country into Uganda to try to go to safety. 9 hours of actual driving because there was lots of stops along the way. So I'm giving this function for the motorcycle trip so that we can talk about the substitution method with an interesting function. So the motorcycle trip, I'm going to use this on your handout now, a V of B of T. You can stop and think why I might have called these things V and B of T. V, you might guess, is for velocity, since we've been dealing with velocities as a common rate of change function that we might integrate. B, you might not know, but I'm going to call that the bumpiness function, and that's why I just picked a cosine function to kind of jostle up and down and show a little bit of those bumpy roads. So this really is a composition of functions, and that's what I really wanted. And so we have V of B of T, so B of T is going into the velocity function, equals 19 times B of T. So V is a pretty easy function. It's just 19 times whatever you would put into it. So if we put all those together, we would have 19 times cosine of 2t plus 1. And we have this composition of functions really twice because cosine of 2t plus 1 is going into 19. We also have a composition of functions here with cosine of 2t. So that was really my goal, to get something that had composition of functions, because that's why we're going to use substitution method, is whenever we have a composition of functions. So my goal in this problem, and the problem I want to solve, is to find the total distance that was traveled in that 8 hours. So we're going to know as a check, kind of on the, like on the project when you had your check of what is the actual value. I know the actual value is 151 miles, but how would I find the total distance then? How would I set that up? Think for a minute with what that integral would look like. Oops, I already gave you a little bit of it. It's going to be an integral, right? So we know it's going to be an integral. I'm integrating what? The velocity, right? Because I'm going to integrate a rate of change. And if it's traveled in 8 hours, I'll just make it easy on myself and call the beginning point 0 and go up to 8. So before we tackle, we'll come back to that example down here. So I'll just put this as kind of our goal, that we know we're going to want to look at this integral. The integral from 0 to 8 of v of t, which will be equal to the integral from 0 to 8 of, and remember that integrals are like super summers, so if I'm integrating 19 cosine of 2t plus 1, your first thing you're going to want to do is to factor out that 19, because that will make our integration easier. So anytime you have a constant times the whole function, do factor that out. So then I have this as my integral, which looks pretty good. If this were just straight a cosine, I could go ahead and integrate that. Our problem is that this is a composition of functions, and so that's the topic for today. So I'm going to do this pre-example right here, and go back and think back to section 6.4. You might not remember that particular section number, but that was the second fundamental theorem of calculus. And so I want to think back to that day. And you might remember we looked at these two integrals and we said, which of these two, if you were pressed against a wall and had to integrate one of those, what would be your function that you would be more likely to be able to integrate? And if you remember back, this one, although it looks easy, e to the negative x squared, it actually ended up being very hard to antidifferentiate. So that one was the predecessor to the function ERF that we remember we set up as something defined to be an antiderivative function. So instead, although this one looks a lot worse, it's actually the easier one to integrate. The reason being that here we do have a composition of functions, e to the negative x squared. That's my composition of functions. What I'm going to be looking for is on that composition of functions, the part that was the complication, which here is the negative x squared. I want to see this existing in the antiderivative. Remember that this is the results of differentiating, because this is the derivative function. So this is kind of the results of the chain rule. If I were to differentiate e to the negative x squared, I know that its derivative would be e to the negative x squared times a negative 2x. So this is actually in a really nice form, and that's what I want you to think about, is think about almost being a backwards chain rule is how we will think about the substitution method. It's like I've got the chain rule kind of all spread out here, and I want to repackage that and go back to what was the original function that gave me this as the derivative. So the form that I'm going to be thinking of over here is the integral of, and I'm just going to say f of something, because that something is usually just the complication. Up here, the something would have been negative x squared. So I have e to the something. That's what I'm thinking about when I say f of something. This is like your complication, what made it hard. And that's the piece that we're going to make a change of variable on, and we call that w. We're going to call that mess, the thing that made it hard, the complication w. So up here, I would call that w negative x squared, okay? Then the other thing that we're going to want in our integral, you can think, okay, I had f of something, that's like e to the negative x squared. The other piece that I'm hoping is also within my integral is going to be the derivative of the something. So here I want the derivative of this w to also exist in the integral. this piece here, along with the dx, and we'll see that in a minute, is going to be dw. So we end up having the form really of integral of f of w dw is what we end up having, or trying to at least view this integral as being in this form. So you can see we're going to make a change of variable. We're going to start with whatever our original variable was, x in this case, and we're going to change it to w. Some of you who may have seen this previously in a high school course or in another Calc 1 somewhere else might have used u for this. We're going to hold that variable to stand for something else in our integration by parts. So you should get into the habit of calling this w for now. So we'll know that all of our w will mean that we're in the method of substitution. Okay, so let's go back up to this example here. If I have w is equal to negative x squared, I need to think about what is the derivative of w. So I'll find dw with respect to x. So the derivative of w with respect to x, it's going to be equal to negative 2x. Okay? Well, we know that this dw dx had an ancestor that was a delta w over a delta x. We went back to the definition of the derivative on probably the second day of this class, and we talked about the change in w with respect to the change in x. If we take the limit as delta x goes to 0, then we get this derivative dw dx. Well, there's some more explanation in the book, and I'm not going to linger there. If you're a purist and you care about this, you can do a little work on this and think about this a little bit more. So what I'm going to do next is I'm going to say dw is equal to negative 2x dx. I can't really do that. I can't really split up a derivative. These really aren't individual pieces, but you'll see if you look in the book, because the derivative had this as the ancestor, once we take limits and things, that's what's going to allow us to do that. The reason I need to do that is when I'm going to do this change in substitution, I need to do a complete change. I need to have everything changed over to this new variable. So when I take this integral here, I need to now change everything with respect to x now to be in terms of w. So when I do that, I have to have a complete change. So I know this part that was e to the negative x squared, that part is going to be easy. So e to the negative x squared is going to be e to the w, okay? I've taken care of that e to the negative x squared. And so, I wish I had a highlighter here. Maybe I'll just use this pink and kind of highlight and know that I've taken care of that piece, okay? What am I left with? I'm left with negative 2x dx. Okay, well, all of that can trade and be dw. So this is what I mean. It's like you have to, I'm going to cross this out here. It's like everything has to have evenly changed using these rules that we have that get us between w and x, from x into w. Well, when we do that, if I've had what I'm going to call a fair trade, then this truly is equivalent to this original integral. It's just in a different variable. We've just made a change of variable. But now we can see this is much easier to solve. So it's helped us to get an easier integral. We know the antiderivative of e to the w is just e to the w, and don't forget the plus c. But now we can't stop there because my original question was this integral in terms of x. So I'm going to want to go back with my w's back to x. So again, I look back to my rule. This is my rule that relates w and x. I'm going to make a change of variable again, and so this will be e to the negative x squared plus c. So that would be my result. And we can see by differentiating now, and this is a really kind of cooked up example, that if I differentiated this, I will get this, because the derivative of e to something is e to something, and then times chain rule, the derivative of the something. So everything's not going to be exactly cooked up like that, and I'll show you that in this next example a little bit, and then you'll work through some more examples with Annie so that you can see more of the ways that this is used. But if we go back to our example here, we can again see, okay, this was almost okay. We just had a little problem right here. So I would say that this is the complication. This 2t is what's causing us a little bit of trouble. So whatever the complication is, will be your first guess for what W is. And this does take some practice in figuring out what W should be. And that's what I'm going to have you do on this next part, is kind of think about what should W be. So don't worry about it. There's a limited number of ways that you can pick W. So just try it out. So here, W is equal to 2t seems like a good place to start. If I would do the next piece, dw dt, in this case, since my variable is t, would be equal to 2. So that means that dw is equal to 2 dt. So these are going to be my rules that will allow me to get back and forth between my two variables. When I look at my expression this time, last time I'd really cooked it up, so I had negative 2x dx within my integral. Now I don't see a 2 here. I know some of you have done this in kind of funny ways. You think, how could I make this all work? I'm going to say instead, look for what you have. I just have dt here. I don't have 2 dt. So that's what I want to solve for. I want to solve this equation here for dt. That would mean that dt is equal to what? 1/2 dw. Okay? So find what you have, use your equations and solve to get something that you can do this fair trade on. Well, now this is all ready to go. So I can say that this is equal to 19 times. And now in this point, I'm going to say t is equal to 0, just to remind myself. And you need to do this if you leave your limits like this. And I'll show you in a minute another way that you can handle this. But if we are going to leave those limits, those were in terms of t. So I need to write a little t here equal to 0, because the rest of the integral I'm going to turn into an integral in terms of w. So now I just start doing my fair trade. 19 was just 19. I've got my limits here. The next thing involved is cosine of 2t, which turns into cosine of w. The plus 1's still just a plus 1. And now the dt, I see, okay, dt is the same thing as 1/2 dw. So I could put a 1/2 dw here, or I can just say, okay, I've got the 1/2. I'm going to throw that out front since I know I can throw constants out front. So that simplifies down to this, okay? So I'll carry along down here. So I have 19/2, and now I can antidifferentiate cosine. And I'm going to get sine. Think the derivative of sine as cosine, so I don't need a negative in front of that. So it'll be sine w. The antiderivative of 1 is now going to be w. And then I'm going to evaluate this from t is equal to 0 to 8. Okay. So then I'll have 19/2, and now remember these limits were in terms of t, so I need to change w back to t. So I'll have sine of 2t plus, and in place of w, I'll also have 2t. And that whole thing I need to go from 0 to 8. And now those, I can drop my t is equal to 0 because now I have the same variable. So now I'll have 19/2, and then I'll have sine of 16 plus 16 minus, be careful here with your sign, put in the negative sign. I like to put a parenthesis there so you don't forget to distribute that. Sine of 0 plus 0, okay? So I'm just going to get 0 out of that. Sine of 0 is 0. So I could throw into my calculator 19/2 sine of 16 plus 16, and you get about 149.3, and this was in miles per hour for my rate. So when I integrate that, miles per hour times hour will give me miles. So I'd be 149.3 miles, and if you remember back to the original, it really was a distance of 151 miles, so my estimate's pretty good. So I want to just step back and look at this a little bit more and take this back to this point in the process. So back up here. When I'm at this point, remember that I had my limits in terms of t. Sometimes you'll want to do it this way, and if you do choose to do it this way, help your TA, help yourself, just remember to write t is equal to, because I've got mixed variables then. It reminded me that I need to go back in terms of t. But we can take this
I'm going to go underneath here, and I'm just going to write a big or, because I could have at this point instead converted everything to W. And for different problems, you're going to want to know how to do it both ways, because sometimes it's helpful to have it in terms of the original variable. Sometimes it's easier to just change everything over to the new variable, and then you don't need to go back. So in this case, I need to think when t is equal to 0, what would W be equal to? Here is where I need to remember that this rule here, almost right, that's a rule, that's relating W to t. So this is always the way that I can convert everything. So that means these limits as well. When t is equal to 0, I'll plug that into this, and I'll get that W, and I'll write it here just to emphasize it, but if I were doing this in a problem, I wouldn't write W anymore, because everything is going to be in terms of W. But W will now be equal to 0, right? Because I'll put 0 times 2 to get 0. If I were at t is equal to 8, my value will be 16. And so now I have this new problem that has been converted completely over to W's, which means I'll never have to go back. So you can see how this would carry through. We would get sine of W plus W, just like we did last time here. But now we're going to go from 0 to 16. Now it just simplifies the process. I don't have to go back to t's, so I can say 19 halves sine of 16 plus 16 minus sine of 0 plus 0. And notice that I get the same thing. So I would likewise get 149.3 miles with that. So know both methods, because for some problems it will be easier to do it one way or the other. So I'm just going to read to you the next part of the handout with the hints. And then Annie's going to help you with some of these, but let me just talk about some of these hints a little bit. So for the first part, hint 1, put as much into W. So this is going to be giving you some hints with how you can figure out what I should call W, because for substitution method, that's really the hardest part of this. Sometimes it's going to be very obvious, but I'm going to give you some different forms when you work with Annie for understanding when you just have to kind of watch for, oh, this is another way that we use substitution method. But here's some general hints. First, you're going to want to put as much into W as you can without making it too complicated. You'll see that in some of these examples below, in particular number 2. So put as much as you can into W. You basically want to simplify your integral as much as you can, but you can't put too much into it. So this will be a little bit of an art that you will learn how much to put into W and how much not to put into W. Number 2, make sure you can differentiate W and you have it covered in the integral. Up above, when we had W is equal to negative x squared, we knew the derivative was sitting there. So you'll get used to seeing that as well. We've got to have the derivative of W covered in the integral. It's got to be sitting there. Again, it's like taking the chain rule, and it's the result of the chain rule. Everything has to be there so you can repackage it back up into the original function. Number 3, make a fair trade. So this is what I mean by you have to, when I took my pink pen and I crossed out parts of the integral, you have to make sure that you've made a fair trade with everything. And the last one is don't forget dx or dt. Sometimes people don't write that dx or dt. You can see it's going to be very important now because it will tell us what we're anti-differentiating with respect to. Remember that its ancestor was a little delta x or a delta t, and so that will be important. So before Annie starts into helping you through these problems, I want you just to take a moment and see if you can look at each of those problems and write off to the side what you think W should be, thinking about some of these hints up above. So just take 1 or 2 minutes and write out W is equal to, and if you keep going, then go ahead and find dW and see if you can do the fair trade on those integrals. If you've done this before, keep quiet, don't tell your neighbor, because it's really worth the struggle for you to try to figure out what W is equal to. So I'll let Annie take it over from here. We'll try to put this video up so that you could look through it later on as well. We'll see you on Monday.